Okay, here we go. So we are going to use Google Colab, Jupyter Notebook and Google Colab to create that spinal cord model we just did in the GUI. The first steps are installing software. So I made a code cell say install software, exclamation point, pip install neuron and NetPyNE. After that, we have to import the stuff we need from NetPyNE, specs and sim. And we need to create our network parameters object and our simulation configuration object. And then we can define our cells. And so we just have one cell type in our spinal cord so far, a motor neuron. And this is directly from our the GUI work we did earlier. And it's down here. So I just copied and pasted the definition of motor neuron into cell types. And then we have to define our populations. So in the GUI part, we made 3 populations of motor neurons: a hip population, a knee population, and an ankle population. And so we're going to add these 3 populations to our programmatic model here. Looking again at the population parameters, the name is arbitrary. You can name whatever you want. I call them hip, knee, and ankle. Cell model is a tag that you could use to specify things later. So I could say, well, these hips are a special type. So when I call that, I can only connect to this special type of cell type motor neuron. We're just going to do 50 cells of each. And the distribution is important for the spinal cord because, there's a very small space laterally, but a very long space vertically. So for all of these populations, we're going to put them between 0 and 100 microns in X and Z. And then Y will represent our spinal cord vertically, and we'll stretch along 500 microns, half a millimeter for each of these populations, overlapping. So 0 to 500 in hip, 250 to 750 in knee, and 500 to 1,000 in ankle. So I'm just going to copy all of these guys and paste them into define pops here. Shift enter. No crash. Okay, so we've done our cells and our populations. If we want to connect them now, we're going to have to look at our synaptic, create some or specify some synaptic mechanisms. And again, this is a dictionary that holds more information, a nested dictionary. So yeah, let's go back to our spinal cord here, and below this, we'll add a text cell that says specify synapse. And in here, this is where we want to define our synaptic mechanisms. We're only going to use one for right now. Motor neurons use acetylcholine as their neurotransmitter, both at the muscular junction and internally in the spinal cord. And we're just going to use a very simple built-in model, exp2syn, a double exponential with a fast rise time and a slower decay time for this. And as I mentioned earlier, this is a toy model. I'm sort of making it as close to a rat spinal cord as I can, the numbers, but it's a toy model that should later be filled in with real data. Great, so we've specified our synapse. We called it ACH for acetylcholine. We got to specify the mod file it's going to use. This one's a built-in. And this mod file has 3 parameters we can change: the rise time constant, the decay time constant, and the reversal potential. And we'll just, yeah, those are pretty standard. We'll leave those as they are. Okay, so back to the tutorial. Once we've done the synapse, we could add stimulation, but we haven't really connected yet. So we're going to connect first, and then we'll add stimulation at the end. So yeah, here we're going to, and are people following along? I hope. Is this working for everyone? Sweet.
Yep.
So we're going to add a text cell that says specify activity. And we're going to use that first connectivity model we did, which just connects all the cells to all the cells. They're all motor neurons, so if we use pre and post MN, it's just all to all. Sins per con, we're just going to use 1. This can be a string function. Weight, we're just going to go with the constant for now, but we can make this a function of other parameters. And same with probability and delay. We're just going to put this in as the connectivity. And yeah, you'll notice just like we did in the GUI when we specified connectivity, you have to specify some general stuff. And then you have to have the conditions for the presynaptic cells and the conditions for the postsynaptic cells, so you know what's being connected. And that concluded successfully. So then we'll do stimulation and then simconfig. But first, we've got our cells and our connectivity. So let's go ahead and run this and take a look. I always like exploring models. So we're going to add a text cell saying explore. That's enough. And in well, hold on. We have to actually we have to define some simulation configuration before we can even do this. So let's do that first. Instead of explore, we're going to say simulation configuration. And yeah, so here, and again, this was just exported from the GUI when we built up the spinal cord model. These are the only options we have in simconfig. We got a duration, and we want to do an analysis automatically. Yeah, we won't even do that. We're just going to set a very short duration. 1 millisecond, because all we want to do is see the cells and the connectivity. So shift. And
Joe, just to mention that all the simconfig options have default values. So if you don't fill them up, they will have whatever the default values are.
Yeah. What is the default time? Is it 1,000 or?
1,000, yes.
Yeah. So it's nice to bump it down if we're just looking at connectivity. So now we'll add a text cell that says create and run. And this is where you can, this final line in the output of the GUI is commented out because the GUI doesn't want to run it automatically, but we need to uncomment this in order to run our simulation. So I'm just going to copy and paste that last line. This is a wrapper that does a lot of stuff automatically. It creates, simulates, and analyzes. So there's commands to create, and there's commands to simulate, and there's commands to analyze. This just as a basic of all of that to make it quick and easy. We're going to hit Shift-Enter in there. We see it's making a network of 3 cell populations, 150 cells. It ran it. Nothing crashed. Awesome. So now we can explore connectivity. Yeah, so whos is an IPython command that shows you all the variables available in your workspace. So we can see we've got the netparams object and the simconfig object that we created, and those are from specs. The new thing is this sim. And this is sort of a master object in NetPyNE that allows you to access and do anything. And what we're going to use it for is we're going to use it to plot the location of the cells and the connectivity. So we're going to say sim dot, and I'm just going to type AN, and it's going to pop up a couple possibilities. I'm going to click sim dot analysis, hit dot again, and I'm going to type PLOT, because that's going to bring up all of our plot options. So sim.analysis.plot. And first, let's look at the 2D net. I might have to say show fig equals true, but I might not. I do. And also, it spits out the output. So we're going to modify this a little bit. a semicolon at the end of a line in a Jupyter notebook suppresses any return. So that semicolon will keep all these numbers from being spit out. And then in here, I'm going to put show fig equals true. Oh, I did not do, there's a couple lines of code you have to put in to be able to see output from these. Crap. Salvador, do you remember what that is?
Is it import matplotlib before everything or something like that? Let me check.
Yeah, I'm trying to remember the last place I did that. Oh, it must have been in one of the tutorials I just did. Matplotlib inline, so that should do it according to what I've got here. Yeah, so we're going to want to I'm just going to do it down here. We're just going to keep a running running log here. So let's do OpenAppleV matplotlib inline. So that's yeah, %sign matplotlib space inline. And that's a magic command that forces matplotlib to spit the figures out right into your notebook. So now let's try this Symbot analysis again. Shift enter. Ah, good. All right. So yeah, with that matplotlib inline, when we do a show fig with plot2d-net, this is what we get. We see the hip, the knee, and the ankle. And we can see they're overlapping. Yeah, I can see why the GUI didn't want to draw the lines, because there's lots of lines for the connectivity. And now let's look at the sim.analysis plot con. Okay, so this is the matrix plot of the connectivity. I'm going to try without show fig just to see if it does it without that. Okay, so yeah, here's our connectivity matrix. It's all pretty much the same, just a little bit of random variation. And now let's do sim.
How did you get the images to show up?
I had to enter this command, %sign matplotlib space inline, all one word. Okay. And that tells the Jupyter notebook to pull them right in and display them. So yeah, so here's the population connectivity matrix, and so we're going to do sim.analysis plotcon, and whenever you're in IPython, you can add a question mark at the end of whatever you want to do, and hit Shift Enter. Now we can see it's got a signature over here, plotcon, include pre, include post, all this stuff. We've got some nice documentation kind of explaining what all these things are. And yeah, anyways, you can explore that later. But right now, what we want to do is group by equals cell, I believe is what we want to do. Let's just try it. Oh, yeah, but if it's grouped by cell, then you can't measure strength, because strength is an average weight. Yeah, you can just measure weight if you're doing this cell by cell. So yeah, so we did plot con with group by equal to cell instead of pop, and our feature is weight instead of the default, which is strength. So here we can see our presynaptic cells and our postsynaptic cells, and it's just a random throughout the whole population. Okay.
Joe, maybe you can increase the size, the font size a little bit in the reader notebook.
Larger?
Yeah, if possible once. Yeah.
Okay, that good? So yeah, plot con, group by cell, feature equals weight. And yeah, we can see it's not really what we want to see, because we'd expect to see a very solid line down the middle with a little fuzz off the side of that diagonal line instead of this. But we're gonna build up to that. Okay, so that was the connectivity. Now we want to add a stimulation, because right now these cells are just going to sit there doing nothing. Give me 1 sec here. This goes till 450. Okay. So yeah, let's add stimulation to sort of kick things into gear and see what happens. And I'm not sure we added a stimulation already on this. I don't think we did. Great. So we are going to, we don't even have this in our output from the GUI. We're just going to add this programmatically on our own. We could use a NetStim, labeled background. Yeah, let's go ahead and do that. NetStim. So what we need is stim source parameters and stim target parameters in order to do this. So from here, I'm going to copy this, and we're going to put a text cell here, which says add stim. I'm going to paste in that. I'm going to sort of make it a little more readable. Okay, so we're going to add a stimulation source. We're going to call it BKG for background. You can make up, you can call it whatever you want. It's going to be a NetStim with a rate of 10 hertz, and it's gonna have a 50% noise. So instead of 10 hertz, it's going to be allowed to vary up and down from 10 hertz to make it a little noisier. When we have the stimulation source parameters, that stimulation has to go somewhere. So we have to put in stim target params. So I'm going to copy that and paste it over here. And again, I'll try to make it a little more readable. Okay. So we don't have PYR, we've got MNs, so we'll do background to MN. Source will be this BKG, and this name has to match the name we gave it. Conditions, the cell type it's going to go into is MN. With a weight of 0.01, we'll give that a try and see what happens. A delay, I don't care. And the SynMech, we don't have an excitatory SynMech. We've got the ACH, capital A, capital C, lowercase h, which we defined earlier. So we've got our stimulation sources and targets. So we've got our connectivity. We've got our sim config, or enough for now. And yeah, so now we want to create, simulate, and analyze it. And again, there's a very simple wrapper that you can use to do that. It's the same as the one we got from the GUI output. And these two things are equivalent. NetParams equals NetParams, SymConfig equals SymConfig. You don't need to specify the names, but we will. So we're going to go back to here, and we're going to say, add some text. Say, create, simulate, analyze. And we're going to paste our sim, create, simulate, analyze, NetParams, and SymConfig. And we're going to hit Shift Enter. 3 cell populations, 150 cells. Great, it completed. So now we can explore whatever came out of it.
Back up to the stimulation.
Yes. Here we go.
Oh. I was just finishing copying it.
Yep. Yeah, so call it BKG, NetStim, rate of 10. Stim target params, call it background MN. Background, the cons are cell type. You know, you could have a con that's a pop, so we could just feed this into hip if we want. Oh, actually, that's interesting. Well, we'll try that next. We'll just feed this into hip, and maybe we can get it to drive a wave. We're in exploratory mode right now. You good with the stimulation there?
Yeah, thank you.
I actually have a question for the stim source. We're not specifying the location yet, right? From where the stim's coming from, or those are just the parameters, right?
So a NetStim doesn't need anything. It's a standalone object that that makes cells do stuff.
Oh, okay.
So yeah, it doesn't. We don't need a location for it.
Okay. Thank you.
How is that different from like a current clamp or a voltage clamp?
The stim. Go ahead, solve it, please.
Yeah, so a NetStim is a spike generator. So it just generates spikes, which are events in neuron, and you connect those events or those spikes to whatever target cells you want. And the current injection generates a current, which is a point process that you put inside a cell.
That you have to feed into a specific place.
Oh.
Okay, so we've got everything, and we're gonna sim. No, we already did that. Yeah. So why is this still there? Delete this. Yeah, now we'll just put in a new block that says explore. And now, yeah, so sim dots. Actually, I'm going to do a shortcut and say SA equals sim dot analysis. That way I don't have to keep typing sim dot analysis dot whatever. And then I'm going to say SL. Let's do shift enter on that. And I'm going to SA dot plot. We already saw the 2D nets. Let's look at the con. Okay, so we got this connectivity matrix here, and we can see that. Oh, great! Now that the background drags it all down to near 0, we can see that all this connectivity is essentially the same. It was set from the same thing. Any differences are just a little bit of random differences. Yeah, let's do SA.plot raster, for example, but I don't think it's spiked at all. So yeah, there were no spikes available. So yeah, we've got our network and our simulation configuration all defined, but we want to kick it into gear. It doesn't do anything. So we're going to add a stimulation. No, we already did that. Okay, maybe it didn't do enough. Okay, so we've got background. 5.5. Maybe this weight is too low. Okay. Yeah,
Sorry, did you change the duration to more than 1 millisecond?
Ah, good, yeah. Duration. Oh, okay. So that's in the stim source params. It's just not listed here, right?
No, in the simulation configuration, the duration of the simulation, I mean, in simconfig, I think you set it before to 1 millisecond.
Okay. Yeah, let's just do simconfig dot. What is it called? Solve it off the top of your head.
Duration.
Let's
check the value, see if it's actually 1 second.
Oh yeah, let's just see what it is. Yeah, it's only 1. That's the problem. Let's set that to 1,000. Shift enter, and then we'll copy and paste sim.create, simulate, analyze. V, Shift Enter, making connections. Uh-oh. Neuron syntax error. Oh, we got spikes this time, though, so I don't quite know what happened there. Any idea what this means, Salva?
Never seen it.
Yeah, me neither. But now we should be able to do sa.plot raster. And yes. Again, it spits out the data necessary to build that plot. So you can either, scrolling up here, sorry. You can either say some dummy variable equals that, and you know that all that data will just go into the dummy variable, or you can put a semicolon at the end of the line, and then you don't even need the dummy variable. The semicolon will suppress the output in IPython and in Jupyter.
You have an epileptic network, Joe.
Yeah, I see that. Yes, this network does not look healthy. It's very spastic, but it's a good start. And yeah, we're going till 4:50. We have another half hour, so great. We'll keep going. Anybody? Yeah, let's make this a little more interactive. Does anybody have any idea why this network would get locked into this strange pattern?
Are the weights that we have are maybe too high?
You know, the weights seem okay because you know they cause a spike. They cause a spike. We're not seeing any dramatic problems there. My guess is that there's not enough diversity. All these cells are exactly the same. They get exactly the same input. They have exactly the same delay, and so yeah, they're going to get locked in to this pattern. So yeah, so my suggestion to sort of break this up and make it look more reasonable is to add a little variability.
So Joe, I think the weights might also be a bit high because
Weights might be high too.
Or to 0.1, which is like in nanosiemens is very high.
Okay.
But it might be a bit of both things.
Yeah, exactly. Great. Yeah. So yeah, let's try reducing this. And going back and changing something and then going back through is bad practice, and it might not work correctly. Normally, when you make changes, you want to go back and sort of start all over again clean. But we're gonna try this rough and dirty. Shift Enter, sim create, simulate, analyze.
What did you just change there? I missed.
Oh yeah, sorry. I changed the weight in stim target params, and I changed it from 0.1 to 0.01, just to see what a factor of 10 difference does.
I think I already had 0.01, and it's still very.
Oh, okay.
My result looked very similar to yours, so we'll see what you get.
Okay, so I did sim analysis. Say that plot con should be the same. Plot raster might be different. And again, I forgot to add a semicolon. There we go. All right. SA.plot raster semicolon, shift enter. Yes. Yeah, it looks like no, the lower value definitely made the spasticity later, but we're still getting into this very regular pattern. So I think we need diversity in the nervous system is incredibly diverse. No two neurons are alike. Each one is a little bit different. And it turns out that for models to be interesting or to be robust, you need that diversity. You can't have a bunch of clones and expect reasonable output. So yeah, there's, let me just check the tutorial again. I think we've gone through all of tutorial 2. Yeah, we've worked our way through all of it. So at this point, we're just playing around. And yeah, so we want to induce some diversity here. Let's see here. I'm looking at the spinal cord.py just because that defines our model here.
Can I just clarify something?
Anything.
So the weight that you're changing when you're changing in the stim target params, that's the spike generator onto every whatever neurons it's connected to, which I guess here is all of them.
Yep.
But right, okay, rather than the synaptic weights between neurons.
Right, but the NetStim is using ACH, so it's using that weight feeds into ACH to activate.
Okay.
Right, where's our stim here? Oh, we didn't add it here. Oh, well, let's just do a quick. Yeah, let's play this. We'll go to File. We'll go to Download. Download.py. Spinal cord. I'm going to put it on the desktop. Spinal cord.py. Oh, no, let's do spinal cord. Do. We'll open that up.
And Joe, can you also save that to the Google Colab to the G Drive or something so we can access?
Yeah, I'm gonna clean this all up tonight once we're done, and then yeah, I'll put nice files in for everyone. Now you can see that it added the. Oh yeah, this is all the commands we put in. So where did we add the stim? Oh, here we are. So yeah, stim source is the background NetStim, and the target uses the Synmech ACH. So the source just causes ACH to pulse on whatever nerve it's attached to. Yes. And now we want to add a little diversity into our cells. And one thing we can do, which will make a lot of diversity very quickly, is this delay of 5. Things will get locked into 5 millisecond patterns. And it's ridiculous to have a delay of 5, no matter if a cell is right next to it or all the way down the spinal cord. Really, we want that delay to reflect how far apart these two cells are. So here we are going to use a string function in the delay. And we are going to say we want it to be, I believe, I'm going to ask Solve about this after, right? CFG.prop velocity divided by 3D dist, or dist 3D.
Joe, but do you want to do this on the Colab?
Oh, yes. I was just going to put it here real quick, type it, and then copy and paste over.
So prop velocity is something that you need to define in NetParams.
Okay.
So it's like a user-defined variable. So you can do NetParams.prop velocity, whatever value you want. And then you can use it in these expressions.
So let's define a prop velocity of 150, I believe is the default. And then, yeah, so then dist 3D is what's going to, eventually we're going to put this in. Is that correct, Salva? Do you think dist 3D like that?
I think it's the other way around.
3D
and
dist?
You don't need the config. Yeah.
Oh, okay, great. By 3D dist. Yeah, we can actually, let's go to NetPyNE.
I have a quick question.
Yeah.
So in the GUI, when using the function to string, you didn't need to use the quotations. And then when doing it programmatically, do you need those quotes to make it like a full string?
Yes. So the GUI, what tricked me is the GUI is trying to make life a little easier. You don't have to actually put in a string. You would leave the quotes off and just put in prop velocity divided by dist 3D.
Okay. Cool.
In the future, I think now we will probably see if it has quotes around it, we'll try to remove those, and make the GUI as robust as possible to weird little errors. But yeah, so we want to go into our con params, and we want to make our delay prop velocity divided by dist 3D.
So it's the other way around, Joe? The distance over the velocity?
Thank you, Salva. Yes. So yeah, dist 3D divided by prop velocity. And we're going to, just plug this in up here and try to hope it works well. The delay. So instead of 5, we're going to paste in dist underscore 3 capital D divided by prop velocity. Okay. Okay, so I'm going to shift enter on that. And then, let's create, simulate, analyze. We got a problem. Dist 3D is not defined. Uh-oh, dist 3D is not defined. Dist underscore 3D. DIST. Velocity. Dist underscore 3D. DIST underscore 3D. Don't quite know what the problem is, Solver. You got any idea?
And maybe the prop velocity is not defined properly.
Here,
Even though it's complaining about this 3D, maybe the expression as a whole doesn't work because prop velocity is not there. You can try a value instead of prop velocity divided by 100, for example.
Oh, great. Yeah, dist 3D divided by 10. Shift enter. Shift enter. Oh, it's the dist 3D the problem with.
Oh, this is sorry. For the stims, we still do not support these mathematical expressions, just for normal connectivity.
It's not on my list of things to do. I'm sorry I brought this up.
It works for me. Oh, I'm not on Colab.
So yeah, delay for the stim we'll just put back at 5 or whatever it was. And I don't want to. Okay, actually, in the connectivity is where I want to do that. Con params. MN. Yeah, so delay here's really where I want to do it. So I want to make this 3D divided by prop velocity. Okay, and then I'm just going to try to shift enter through this. I'm going to skip duration 1.0. And this is a horrible way to do research, but for demonstration purposes, we still don't have this 3D. Oh, did I take it out of the? See, the problem is you should really go linearly in these notebooks. I'm jumping around inside, and so you end up with some problems that can be hard to define. I think I didn't get rid of this 3D in the other thing. Let's see here. Oh, no, delay 5. Let's shift enter that to make sure it went in this. Hopefully this will go. That's taking an extraordinarily long time. There might be a problem. Oh, no, here we go. Get that same weird neuron thing, but it went through. It's got connections and spikes. Great. So yeah, let's see the plot con. Okay. Oh yeah, really what we wanted to see is the raster to see if we got rid of that sort of epileptic behavior. Oh, it looks different. Interesting still. I'm not quite sure how I would describe that behavior.
Is there a way, does NetStim, am I right in saying that it's stimulating every single synapse in this whole network?
We set it up to, give me one second.
Basically. So I think the behaviors we're seeing is normal because you basically have all the 150 cells have a synaptic input as a background input, and then you have a bunch of excitatory connections between them. There's no inhibition, so it's normal that the network sort of blows up.
Perfect.
You get like this very highly synchronized network.
So if we can inject some current into one cell, can we see it
exactly
propagate?
Let's try that now. We'll try to inject a current at one end of the spinal cord and see how that plays through the network.
Or if you also decrease a lot the background and just have it like maybe as a sort of background stimulation that doesn't generate so many spikes, and it's just a low level of stimulation to have some ongoing activity.
All right.
But the current injection also.
But yeah, let's try a current injection here. Clamp, it's usually easier to start from an example. Tutorial. Okay, yeah, delay, amp. Okay. So let's just copy this whole line, stim source params, and in our collab here, we're going to paste that netparams.sim source params. We're going to just call this iClamp1. Type is an iClamp. Yeah, we'll leave it a delay of 300, duration of 100, fine. Amplitude, let's just set a constant for right now. 0.1, I think, is pretty decent on this. But we'll see. So that's our stim source params. So now we'll need a stim target param. And we'll just copy this. Let me make this a little easier to read. Okay, so we got our stim source. Now we'll get our stim targets. Call this iClamp1 to. Should we feed it into one cell or the entire hip? One cell. So iClamp into cell 0. The source will be iClamp1. And let's make this easier to read. Source iClamp.
When you specify net params, stim source params, and then you do your iClamp, is that going to overwrite your stim source params that were the background?
Not unless we use the same name. So the other name was something different. And this stim source params is just the dictionary. So I've just added another key and value to the dictionary.
So you have to take that away. Otherwise, when you run your stimulation, you're going to get both at the same time, right?
Oh, yeah. I was going to leave the background on and see what happens.
Okay, yeah, fine. I'm just as a...
Yep. So yeah, delay of 300 is fine. Duration of 100. We're just playing around right now. So we'll leave that iClamp1 to cell 0. Source iClamp1. That's what the middle of the soma. And cons, we want a cell list. And we just want to use just one cell 0. So, oh, invalid syntax. I got an extra bracket. There we go. Shift enter. Okay, so now we want to create, simulate, and analyze. All right, good. It's successfully completed. So let's plot the raster. I remember to do the semicolon at the end. Okay, so we delayed it by 300 and we're not seeing anything. We're just putting it into one cell. I'm going to put it into all of HIP and I'm going to crank up the amplitude.
So maybe if you reduce the background, you will see more of an effect of the current injection.
Okay. How would you reduce that? You mean the amplitude?
The connectivity weight in the STIM target params there, so 0.01, you can reduce that one.
Another factor 10.
Maybe that's, yeah, you can try. And you can increase also the amplitude of the current injection, so maybe 0.1 might not be enough to trigger a spike.
Yes. Right.
Semicolon.
There we go. Okay, well, so we turned off the noise completely, basically, and we input in at 300 milliseconds, spreads instantly across the network, and then, you know, the delay and hits again and again. I'm not sure this model's entirely clean and we've got everything in the right order and everything. So I'm gonna, once I'm done presenting this, I'm gonna go through, clean this all up, make it more linear, and I'll share it with you all. So that you have access to it. But yeah, so this is a nice way. We're going to work with Jupyter notebooks and eventually on your own machines do all this stuff, and you can interact back and forth with the GUI. You can import a Python script into the GUI. You can export a Python script from the GUI, and yeah. So yeah, I think I'm going to sort of conclude here. Any questions or discussion here? All right. Well, thank you guys.
Thank you so much, Joe.
Thank you.
So we'll
Thank you.
Thank you.
We'll be back in 20 minutes
Thank you.
at 5 to 7 to do some exercises on what we learned today. Thank you.
Yes.
Thanks.